I need to do it.
Yes, it is.
I don't need to.
No.
Doesn't need
No.
Okay, so if you have tried this before, hold on. It's taking too much time. Okay. Has anyone tried this? No? So it should be quite popular in Facebook, Instagram. So it's a very new AI technology being developed, and it's free online. It's called the GPT. I don't know what does GPT mean, but basically it's a AI system that can chat with you, and actually it can teach you something. So let me show you. So I just asked him a very professional question. Suppose you should know. I said, explain maximum shear stress model to me. So it's an AI system being built based on the well-known knowledge from internet, both technical and also social life and everything. You can even ask him to solve a math problem. Just ask him to find the minimum point of a function using Newton's method. It will tell you how to do it. So from now on, you don't need me. You can just ask AI. It will teach you how to. And it's really doing a pretty good job. I'm very surprised by this. But because it's free, so the answer could only have certain length. There's a limitation. So when this AI system found a longer solution, if it's over the limit, it will stop at some point. But you can ask this system the same question multiple times. It will try to search the internet for answers again, and it may give you a different answer. So it's quite powerful. This time, it's showing me one example. The last time I tried, it didn't show me an example. Okay, so remember last time we have in gear design we have a model called Lewis factor. Let's see if AI knows. So, do you know Lewis factor in gear design? Oh, he doesn't know. Okay. Maybe it's too specific. It's some method inside the textbook. It's not a well-known knowledge from the internet, so he couldn't find it. Or if I type in the information more precisely, maybe if I use Louis formed that. Maybe with that he knows. See. Don't rely on it 100%, but it's a really quick way for you to search for some basic explanation of something. Don't use it to do your homework. Don't use it to write your thesis. Okay. So today, you guys are still working on your project, but I would like to tell you more about mechanical design. But we only have very limited time, so I would like to just briefly talk about one of the components. Okay, maybe I talk about, let's see. I think it will be quite useful if I introduce something about bearings, because it's a quite important subject in mechanical design. If you want something to rotate, almost every time you need bearings. Let me see which chapter. Okay, yes. So bearing is a study. I mean, it's a kind of design related to lubrication. What is lubrication? It's 润滑. So inside the bearing, we have, for example, if we have ball bearing, we have small metal balls inside the bearing. Let me show you a picture. This one, not this chapter. But this is journal bearing. Okay, next chapter. So this is gear. Okay. Let me check. Okay, rolling contact bearings. Okay, here. So a bearing has those metal balls inside. Sorry, and we have inner rings and outer rings. Okay. And some other terminologies you can. The inner parameter, okay, it's called the bore. The inner hole is called the bore, okay, and the outer diameter is still the outer diameter. And ball bearings could be made in many different types, okay. So, yeah, we cannot spend too much time on this. We do have roller bearings. They are like cylinders, okay? this is a cylinder right here. And we could have cone-shaped rollers. When you see this one, it's actually a cone. 圆锥, okay, a cone. It's not a cylinder. It's a cone. And it could be having some angle. When you have a roller that is having an angle like this, that's because you want this bearing to be able to carry loads from different directions. Okay, and we even have this is also a cone shape lying on the circular surface of the bearing. Okay, and this is more like this is like a multiple straight thin rods form into a circle. Okay, you have many of those, and that's why he used the name needles. They're like thinner cylinders, multiple of them. Okay, so there could be many kinds of bearings with different geometries inside, and it's rolling. So when you design a gear, the force distribution inside the bearing is so complicated. There is no exact force analysis to predict or to estimate what's the force inside. I can show you. Let me see if this PowerPoint has it. Just very quickly finding what I'm looking for. Okay, in the other one, just quickly to explain some very important idea of gear design and why we design, so not a gear, bearing design, why we design the bearings in such approach. This one should have it. Let me see. Okay, maybe I find a picture from internet. Okay, so the stress distribution inside a bearing is very complicated. Like this is already a model. A model is not the exact shape. And this is someone trying to analyze by finite element methods. Like this one. The deformation is kind of exaggerated, but you can already see how complex the stress could be distributed inside bearing. Okay, so those are, okay, this is a different one. Let me see if there's some more supporting information that I can show you. Okay, so like this is a diagram of showing the stress distribution inside bearing in different angles, and you can see those curves. If it's having a wider radius, it's larger. If it's smaller, it's lower. Actually, the last picture was much clearer. Okay. Oh. maybe this. Yeah. So from here you can tell the stress inside the bearing around the entire geometry is so nonlinear. So what can we do to properly have bearing design? So the strategy is we don't try to find the good way to analyze the stress. We rely on statistics, 统计 statistics. Okay. So what's happening is there are researchers has done a lot of research experiments and figure out there's a relationship between two important things, F and L. F should be the load being applied to the bearing. L should be life. They found F and L has a relationship. If you want to have a longer life for your bearing, you cannot carry a larger load. If you want to carry a larger load, then the life of the bearing will be shorter. From common sense, it sounds really simple, but they found this exact equation and they did experiments and realized, okay, this truly could be considered as the design equation. Okay, and of course, this A parameter could be changing for different kinds of bearings. Like in this example, in this textbook, it mentioned, okay, for ball bearings, this power is 3, this is 10/3. How come it's 10/3? Because in their experiments, they found this parameter is the best fit. For statistics, it's all about fitting the coefficients. Okay, and there's no exact stress analysis or force analysis for bearing. They just believe or they observe the behavior between force and life, and maybe from experiments they found, okay, if I take a logarithm of force and take a logarithm of life, the experiment data looks like a line. So probably they can use linear regression to get this line. And this is their result. Okay? So with this, it's very useful because they found this FL to the power of 1/A is a constant. FL 1/A is a constant. So that means if I have a condition 1, this is condition 1, must be equals to condition 2. Right? So sometimes, if you have experiments for some condition, but you want to check how this bearing will behave in a different condition, then what you can do is you can, let's say you don't know, okay, let's say this is known. You know these two parameters because you have purchased the bearing and you know some data is known, but you don't know about how this bearing will behave in a different condition. So maybe you want to apply a different load. Then use this equation. This can be calculated. You can estimate what's the life for that bearing. So this is how you can use an equation like this. Maybe this particular data is not provided, but they tell you this. You can plug into the equation to estimate the behavior. Okay? This is exactly what I'm talking about. Okay? Exactly what I'm talking about. So, based on this, there's a very important terminology called C10. What is C10? What are you talking about? Okay. So C is like a rating. So it's catalog load rating. It's like a score. And C came from this catalog. Okay. What is 10? 10 represent failure rate of 10%. Or you can say reliability, 90%. Okay. So what does reliability 90% mean? That means if you have 100 exactly same bearings, after you finish a lot of works until the end of its life, 10% fails. That's reliability. So for example, you estimate the life of this kind of bearing equals to, for example, 10,000 rounds. So just one example. Let's say under, for example, under some load, F. So if I have a bearing under some kind of load, F, and if I rotate 10,000 rounds, by the equation I mentioned, maybe this load tells you 10,000 rounds, this bearing will be dead. But in fact, what you get, the number 10,000 round, doesn't mean all the bearings will die at the same time. Those bearings doesn't die when you are moving on to the 10,001 round. It's just indicating when all those bearings reach to 10,000 rounds, around 10% of the bearing will fail. So this is really a statistical approach. Statistical. Okay. So this kind of research just tell you statistically when this kind of bearing is carrying some load F after some life, for example, 10,000 rounds, 10% of this bearing will fail. Okay? So in the future, when you check the catalog, when you see C10, C10 represent a kind of force value. A kind of force value. And what is FR? R should be reference, I believe. FR. Oh, I think they use reference for FR, I believe. So basically from the catalog, it's telling you, okay, C10 is a reference load. Okay, and in order to determine, and over here, D is your design. I believe that's what this equation is about. Okay, this is determined from what we had earlier. Then this is from the catalog. The catalog only tells you C10, basically 90% of reliability. What would be the force? But it only gives you one number. What if you are not going to apply the same load? You are applying a different load. That means in your design, you have a different F. So you can plug in that different F, and the book usually will, the catalog will tell you what is the reference life. So you have C10, the book tell you what is its the life in catalog, and then you put in what's your the load that you expect to apply, then you can calculate life. That's basically. the idea. Okay? Very simple. And I hope it's easy for you to understand. Let's check more about this kind of calculation. Let's see if this is showing a table. I would like to show you a table. Okay. So this is what you can find in a catalog for bearing. So usually what you in your design, you of course you will pick up the dimension, right? This is what you usually do. You decide, okay, the cylinder, the shaft at the center is going to be having the same size as the bore. Okay, we just mentioned, if this is your bearing, and this is called the bore, and this is called the outer diameter. Outer diameter. So OD is outer diameter. Okay, so usually in your design, you define the dimension. But once you define the dimension, you already select which kind of bearing you are choosing. Because in this catalog, they only have specific dimension. If you pick up this one, the bore has to be 12, the OD has to be 32. So you can only choose from the catalog. You cannot just design any dimension you want. So so let's continue to study more. If you already pick up one, for example, this one. This is the bearing you are choosing. See how it's giving you the C10. There are two C10s. So here it's telling you this is deep groove and angular contact. So basically there are two different kinds of geometry, and it allows different kinds of contact. So let's just focus on one kind. So let's focus on this kind. Okay. So so C10. Does it? Okay. Usually a book like this will tell you what's L, and usually L probably is 10 to the 6 rounds. So it's indicating, if I'm right, for the bearing to rotate under load for 1 million rounds, the maximum load this bearing can carry is 12.7. I don't know the unit, we need to check more, because this is one slide, it doesn't provide every information, but there's a unit for this 12.7, okay? How about C0? C0, I believe it means like a reliability of 99.9, a lot of nines. So it's almost like 100% reliability. So C0 is like, okay, if you apply a much smaller load, the life could be much, much longer. Okay? For exactly same bearing. Okay? And the other parameters are just talking about the geometry. I think the most important thing about bearing catalog is how much load you are carrying, and you need to estimate, okay, for this particular design, how much circle how many rounds do I expect this machine to operate? For example, you are designing for the UAV. Let me give you one example. Okay. So this is okay. This is a set of propeller on drones, the propelling drones. And over here you see they already prepare the bearings for the propellers. And as a mechanical engineer, how are you sure this bearing is okay? Should I get a bigger one or smaller one? So they must have done some engineering, some calculation to determine, okay, this is the most appropriate one. If the bearing is larger, it's heavier. Heavier means you waste more energy, and maybe it's too strong. If it's smaller, maybe it's too weak. So for UAV, there's definitely research about how much load will be applied to the bearing. You can definitely do some analysis about the UAV, and then you can estimate what's the usual average force applied to the bearing. And use that bearing, use that force, and you want to tell you, when you are designing it, you need to make some estimation about how much life you wish this UAV to survive. So you kind of need to, as a UAV design, you need to know, okay, when it's flying, what would be the rotational speed, how many rounds, and for every mission, how long you're flying, so you have a true time. For example, it's flying for 20 minutes, and what's the average speed of the propeller, then you can calculate for every mission, 20 minutes, how many rounds this bearing has been rotating, has been operating. So for every mission, for example, 1,000 rounds, okay, then how many missions you wish this UAV to operate? 100 missions or 500 missions? So that's how you can kind of estimate life for a component like this. And once you know, okay, I know the force, I know the expected life, and then I go back to bearing selection, like this one. They only tell you the standard measure, standard force. That definitely is not the force you're looking for. Then you can plug into the equation that we saw earlier. Where is it? This one. From the catalog, you have this, and usually the book tell you what is the reference life, maybe 1 million rounds, and from your need, UAV design, you know, okay, this is the force I need to carry, and from the mission request, you know, okay, I probably need a UAV to survive for 5,000 rounds, something like that. So when you plug in, you can realize how is your design is doing, okay? And the good thing about this kind of research analysis, it tells you what's the reliability. If you are following the equation and the catalog, then you can expect, if I have 10 UAVs, maybe one UAV will die when the expected life reaches. Then probably when you are reaching 90% of its life, you can replace the bearings. Then you can avoid possible failure. Maybe the mission is very important. Okay? So if you plot out the linear function that I just showed you, actually it looks like a straight line in this diagram. This is logarithm force and logarithm life. X is also life. So what's happening is the catalog tells you C10, and usually okay, X10 basically is L10 or L reference, because this is F reference, right? So basically this point is the point the catalog tells you. It tells you what is C10, and it tells you what's the life for C10. This amount of force can, under this amount of force, this bearing can survive for this amount of time with reliability of 90%. This is reliability. Okay? Reliability. If you want a greater force, like over here, then you have shorter life. If you want longer life, like here, then you can only carry lower force. Okay, so this line basically is the exact equation, the statistical equation that we showed you earlier. How about I wish to design with a different reliability? So what's happening is you can have different lines. And different lines represent, the parallel lines represent different reliability. So RD is the reliability of your design. So usually, if this line is going down right here, coming lower, do you think it's having a greater reliability or lower reliability? What do you think? So basically we're talking about a point right here. If I have a lower line, this is from the catalog. Basically I'm looking for a design right here. Same force, but with this new line, I actually have a much shorter life. So that must means when this bearing reach this amount of life, it's still having a greater life, greater reliability. So you can say this line is representing reliability maybe 95%. So if you only study this line, okay, let's focus on this line. It's like at the beginning, this is brand new bearing, zero rotation, brand new. So it's like right here I have 100% of life. 100% of we can only say reliability because time is life. In this description, time is life. So it's like now I'm 100% reliable, no failure. As you begin to operate, the operation time increases, a lot of rotations for the bearing. There's a chance the reliability drops. Maybe when you reach to this point, this is already reliability 99%. That means if you have 100 same bearings, one may fail. And down to here, maybe 5% of bearing may fail. And maybe down to here, 10% of bearing may fail. Does that make sense? Okay, so it really depends on how reliable you want your bearing to be. Okay, and that really decide which line you are focusing So in the catalog, it only gives you C10. It only gives you the reference life. It only gives you this point. It doesn't give you anything else. So as an engineer, if you have no idea about this knowledge, how can you design a bearing with different load, different amount of life, different reliability? So you need to truly understand what's going on, then you can make designs out of the catalog. Usually what happens to us, if you don't know about mechanical design, you are choosing a bearing, but you didn't estimate life. That's what usually regular engineers do. They just focus on geometry. Okay, this shape is fine. Because usually when they design, they pick up they already know the diameter of the shaft. And they just pick up, my shaft is 30 millimeter in diameter. Okay, so this must be the bearing to use. This is what usually happens. But a good engineer should precise and properly estimate life. Because in your first several lectures, we already know the bearing is important. Bearings are so important. That's where you have reaction forces. And when you design a shaft, do you remember? We always have bearings, and we always study, okay, there could be reaction forces. For example, there's an external law like this. And when we study the shear force diagram, it's going to be like this, right? So this is where you have shear forces. And location, and in some cases, if you have another bearing here, for example, if you have something like this, and if you have some loads right here, so usually you could be having a design like this, right? So over here, that's where you have a huge change of shearing force. So, and if you take integral, then you have moment. So usually in this case, you may have moments like this, something like that. It could be wrong because I may miss some of the forces. But anyway, bearings carries loads. So if you in so many cases, failure occurs on bearings. I can show you one particular example that we are working on right now. Let me see if we can find pictures. Okay, maybe something like this. Okay, so this is a chemical reactor. So at the center there's a shaft, and it's spinning. And on top of the shaft there are propellers. So for chemical reaction, you need the propeller, the blade, to mix the chemicals inside. And if it's a high pressure, high speed chemical reactor, this is rotating really fast. And of course, there's a lot of force being applied to the shaft, and of course being applied to the bearings. And with a system like this, as mechanical engineers, we can try to place the bearings, probably somewhere here and here, right? There's nowhere else you can place bearings. Then, can you guess what kind of failure it could be getting? Maybe the ball bearing has wear, and maybe the bearing breaks. Then the shaft cannot move anymore. That's where the failure could happen. So for a system like this, I think the most important component for safety is actually the bearing. If you did not calculate if you did not estimate the life of bearings properly, you will see failure out of your expectation. Okay? So it's very important component for design. Because we have very short time, what's the 2 minutes? 3 minutes, yeah. Just a very quick. Okay, so for this book, if there's a homework for this chapter, usually we solve a problem like this. So we try to link the bearing design with the shaft design that we learned in the past. But luckily, you guys don't need to worry about this. But I just want you to know, for shaft systems, you can place all kinds of mechanical components on the shaft, and usually it's rotating. And always you have a bearing if it's rotating, right? So in the chapter for bearing design, what the usual problem is, what's the expected life for the bearing? So it usually comes from force analysis and then life estimation. Or a problem like this could ask you to make a proper design of the bearing based on the table. Which bearing could survive some kind of load with certain amount of life. Okay, so in the future, if you have our textbook, or in the future when you look for catalog or reference information, please don't forget about what I taught you today, or maybe my YouTube video will always be there. You can go back and watch it again. So please remember, C10, what is C10? Because in the catalog, it may not tell you what is C10. C is the catalog, the force. 10 represent 90% of reliability. And usually, C10 has a corresponding life based on the data this catalog is providing. That's the most important thing, I believe, for today. Because in the future, when you pick up a bearing, if you have no idea about C10, you are basically making a guess. Okay? So don't guess. That's what I want to talk about today. And you need to... you need to check your attendance. Phi is preparing the QR code. Okay? So for the following lectures, if we don't have arrangement for final presentation, then it will be a lecture like this. I will be briefly introducing some mechanical component, and I will tell you what I believe that is the most important fact about this design. And I hope that could be somewhere in your mind, in your brain, and in the future, when you get a job and when you need it, you know where to find this knowledge. Okay, that's it for today. See you next time.